Well, good afternoon, everyone, and thank you for joining us today. My name is Oliver Thompson, and I'm your host for today's webinar, the first, in fact, which we've run remotely, so we're hoping everything is going to run smoothly. Our webinar is scheduled to run for 45 minutes, after which we'll have an opportunity to answer some of your questions, and you can submit these by clicking the Q&A button that should be visible at the bottom of your webinar display panel. We'll try to get through as many questions as possible, time permitting. A recording of today's webinar will be available to you all shortly after this event, and we will notify you on how to access this as soon as it becomes available. In this webinar, our speakers will discuss and demonstrate how aged sorption studies for pesticides should be conducted, analysed, and used in regulatory assessment. Also, following the recent review by EFSA, we will discuss the inclusion of these studies in higher tier testing for groundwater. It's my pleasure to introduce today's speakers. Dr. Wendy Van Beinum is a senior environmental fate and modelling consultant at Enviresearch with a PhD in soil science and more than 15 years experience in pesticide fate processes and modelling, such as sorption, diffusion, and leaching of pesticides, and extensive experience in the development of aged sorption guidance. Dr. Chris Sinclair leads the environmental fate and metabolism team at Fera. He has a PhD in environmental science and more than 22 years experience of performing standard and bespoke environmental fate studies in the laboratory, as well as fate and behaviour studies at the field and semi-field scale. So now I'd like to hand over to Chris and Wendy and look forward to an interesting and useful session.
Thank you, Oliver. First, we will start with an outline of the webinar this afternoon. Initially, we will start with a brief introduction on what is aged sorption and some of the history of the guidance development. We will then look at the guidance itself. Initially, we will look at the practical laboratory aspects of an aged sorption study. We will then consider an overview of the Aged Sorption model and theory, how the laboratory data is used to fit and determine the aged sorption parameters, and how these values are then used in the groundwater assessment. Then we'll move on to talking about what needs to be considered when you're thinking about aged sorption. This will include advantages and disadvantages, future developments in this field, and possible testing strategies and options that are available. Then, as Oliver has said, we should have some time for your questions. So let's start with the simple question of what is aged sorption? At the lower tier of exposure assessment, we assume sorption is both instantaneous and fully reversible. This implies that sorption coefficients are constant over time. However, we know that sorption in soil increases gradually, and it's not possible to say where fast sorption finishes and slow sorption starts. It is a continuous process that slows down over time. In the field, sorption will increase rapidly until it reaches the amount of sorption that is measured in a standard laboratory study. Then it'll continue to increase over a period of weeks or months. In the regulatory context, aged sorption is defined as the increase in sorption beyond what is measured in a standard sorption equilibrium study. However, sorption itself, or aged sorption, is not a new concept. There are many papers in the literature demonstrating the significance of long-term sorption. One of the earliest was by Haymaker and Thompson in 1972. This paper looked at these processes in Hawaiian soils. But what we do see in the literature is a range of terms used to describe the process. Aged sorption, time-dependent sorption, kinetic sorption, and non-equilibrium sorption have all been used. One of the earliest reported studies was that of Alan Walker in the late 80s. Here, a field study was performed to measure the behaviour of 4 herbicides in a sandy loam soil. This was combined with the laboratory-based process studies to provide information to allow the behaviour of pesticides in the field to be modelled. Initial modelling estimated the soil concentrations pretty well, but the extent of vertical movement was overestimated. So additional lab experiments were performed that looked at the long-term absorption processes and looked to provide new parameters. These were used in the model, and better predictions of vertical movement of the herbicides were provided. This is shown in the graph on your screen at the moment, with the dotted line being the initial modeling and the solid line being the revised modeling. A variety of models have been presented in the literature that describe age sorption. In the late 80s, Jos Boosten and his colleagues developed a 3-site adsorption model. The first site was used to describe equilibrium sorption, while the subsequent sites considered age sorption over a few days and hundreds of days. Over the next decade, there was a plethora of publications measuring both the change in sorption with time and developing models to best describe those processes. We could trace the history of the guidance development itself back through a range of projects and events. A project was completed in 2004, which investigated the adsorption of 9 pesticides in 2 soils. Standard Freundlich isotherms were established over 24 hours in batch equilibrium experiments, and incubation systems were used to measure the effect of time on sorption. All the pesticides showed some degree of age sorption, but the extent varied on a pesticide by pesticide basis. A subsequent project completed in 2008 by Fera, formerly known as the Central Science Laboratory, collated age sorption data from the literature. After applying quality criteria, 195 data sets were identified, including 28 pesticides and 50 soils. Here you can see the variation in both the KOC and DT50 for the pesticides, as well as the clay content and organic carbon content for the soils. By examining this data set, it was found the experimental methods used influenced the age sorption parameters derived, and the project recommended that age sorption experimentation should be standardized. In 2009, the Focus Groundwater Work Group recommended a tiered approach for groundwater assessment, and age sorption was detailed as a refinement option at Tier 2. Guidance was also provided on how to derive age sorption parameters from age sorption studies using model fitting. Next, the most important project in the development of the guidance was initiated by CRD and performed by Fera in collaboration with Altera in the Netherlands. This project was initiated due to a lack of agreed guidance on how age sorption information should be determined and used. The specific aims of this project were to review age sorption model concepts and the different experimental techniques available, then, using a range of soils and pesticides, measure the age sorption in the lab with the variety of experimental techniques available, to evaluate the effect of experimental methodology, data handling, and parameter estimation techniques when deriving age sorption parameters from the experimental data, and assess whether age sorption parameters derived in laboratory studies were suitable to describe the leaching behavior seen in undisturbed lysimeters. And finally, to draft and disseminate guidance on how age sorption studies should be conducted, analysed, and used in regulatory assessments. As part of that project, an age sorption workshop was held at Fera in 2010. The workshop was attended by regulatory authorities, academia, consultancies, and industry. During the workshop, the guidance was presented and feedback collated. One of the main recommendations was the guidance should be tested against real data sets. This led ECPA to provide experimental data sets and funding for Battelle as an independent organisation to test the guidance. Fera and Enviresearch then critically assessed the testing results, and in discussion with ECPA and CRD, made changes to the guidance and a new version was produced. The majority of the development of the Aged Sorption guidance was performed by Enviresearch and Fera. In 2012, CRD published the draft guidance on their website and submitted it to the EFSA PPR panel for review. Next slide, please. In 2015, the PPR panel were unable to provide an opinion and a statement was provided instead. This highlighted concerns on the interpretation of the experiments and how the results of the experiments should be used. The panel tried to investigate options, but could not complete this activity as they were unable to consider the underlying data in the time available. In 2017, taking into account the points in the EFSA statement, a revised guidance document was submitted to the panel for review. And in 2018, an opinion from the PPR panel was provided. In 2019, the guidance was updated, taking into account the opinion, and a final version has been published on CRD's website, and this has been sent to the Commission for approval. So now we'll move on to looking at the guidance itself. The guidance details 3 parts that are involved in the Aged Sorption assessment. First, there is the experimental procedure, which is the lab studies required to produce the absorption data. Then there is the kinetic modelling to interpret the laboratory data and derive the Aged Sorption parameters. And finally, there is the use of these parameters in the groundwater models to calculate refined groundwater concentrations. We will now take you through each of these aspects. So, to start with the laboratory requirements, we'll first consider the soils. Like other soil studies, the soils need to have contrasting properties, such as pH, clay content, and organic matter content. To implement Aged Sorption, then parameters are required from both Aged Sorption and batch equilibrium studies. The parameters need to come from studies that use the same soil. However, it is not sufficient for soil to be used of the same type or name. It really needs to come from the same batch. Therefore, even if already available, batch equilibrium sorption will probably need to be repeated with soil from the same batch that will be used for the Aged Sorption study. The soils used for the Aged Sorption experiment should be handled in the same manner as soils for a soil degradation study. For example, that needs to be used within 3 months of collection and maintained field moist during storage. As mentioned, if equilibrium sorption data are available, it is highly likely that these experiments will need to be repeated on soils from the same batch. These experiments are needed to determine the Freundlich adsorption exponent 1/n. While we may think we can get away with just performing tier 3 to establish the Freundlich isotherms, information from the lower tiers of these experiments are important to confirm the experimental design for the Aged Sorption experiment in 2 ways. Firstly, within the guidance, there is an assumption that Aged Sorption equilibrium will be reached within 24 hours. This needs to be confirmed for the specific soils. And if it's longer, the time to equilibrium needs to be determined. And secondly, the soil solution ratio needs to be optimized and determined for the specific soils. The Aged Sorption experiment itself is very similar in design to an incubation soil degradation study. And this is why the guidance suggests that in certain situations, soil degradation and Aged Sorption can be performed as a single experiment. Each time point has 2 replicates that are sacrificially sampled. Samples are maintained in the dark at 20 degrees C with a soil moisture of between PF2 and 2.5. Time points are set to follow the pattern of decline, and it's very important to have a sample immediately after application. For the establishment of Aged Sorption parameters, each soil needs a minimum of 6 time points. However, some time points may be eliminated during the data analysis, and this needs to be considered when setting the number of time points. So far, there's limited difference between an Aged Sorption experiment and a soil degradation experiment. The difference is really in how the samples are extracted. Each time point requires 2 extractions, which can either be performed in serial on the same sample or in parallel on subsamples. There is a gentle extraction designed not to disrupt the soil structure to extract the equilibrium adsorption fraction. This is performed with 0.01 molar calcium chloride at the same soil solution ratio as used to determine the Freundlich isotherms. The extraction will be performed for 24 hours unless a longer duration was required to reach equilibrium, and then this time should be used. A solvent extraction is also required to extract the long-term sorption fraction. This extraction needs to be identical for all soils and have demonstrated recoveries of at least 95% at the initial time point. The 95% recovery applies equally to both radio-labeled and non-radio-labeled studies. Radio-labeled test compound would be used in preference, and if it is, then non-extractable residues should be determined by combustion. And now, Wendy will explain the Aged Sorption model and parameter fitting.
Thank you, Chris. So now we have the data from the laboratory study is available. We will then continue the next step, which is the modeling, which we need in order to derive the aged sorption parameters. So first I will show you the model we use for aged sorption. The model is also referred to as a two-side model, as it separates sorption into 2 sites. The fast equilibrium sites, and secondly the slow long-term sorption sites. Equilibrium sorption is described by the Freundlich equation. So we have the sorption constant, the KOM, and the Freundlich exponent 1 over n. So this is the sorption we normally measure in standard sorption studies, and also the sorption we use in standard focus modeling. Then in the aged sorption model, we have the additional long-term sorption, the long-term increase in sorption. So here adsorption and desorption occur at a slow pace, described by a rate constant K-des. And the model assumes that adsorption and desorption are fully reversible, and they're both controlled by the same rate constant. The name K-des stands for desorption, but this is a bit confusing in this case because it's used for both adsorption and desorption. So in the beginning, the adsorption will be dominant, but then over time, when the concentration in solution gets depleted, then desorption will take over, and then desorption will be the dominant process. The amount of sorption that it is trying to reach over time is also described by the Freundlich equation. Only here we use the sorption constant KOM NEQ, where NEQ stands for non-equilibrium sorption. The 1 over n value, we assume that both types of sorption have the same 1 over n value. We use the same 1 over n for both equilibrium sorption and long-term sorption. Now, instead of using the KOM for long-term sorption, the models actually use the fraction FNE, which is the ratio between the 2 sorption constants, the KOM in the non-equilibrium part and in the equilibrium part. So these are the 2 aged sorption parameters we need to derive from the lab study, the rate constant K-des and the fraction FNE. The focus models assume that degradation only occurs in the soil solution and in the part that is bound by equilibrium sorption. And we assume that the pesticide that is bound by long-term sorption is not available for degradation. So this is why in the aged sorption model we use the DEC-T50 EQ, which is different from the normal DEC-T50. So to summarize, these are the model parameters that we will need to derive by fitting the aged sorption model. The Freundlich exponent 1 over n will be taken from the batch sorption experiments on the same soil, as it's not possible to derive the 1 over n from aged sorption studies, and this is why we need those batch sorption studies in parallel to the aged sorption study. So the The 1/n is not fitted, but the parameters we need to fit is the KOM EQ, the DECT50 EQ, the rate constant KDES, and the fraction FNE. There are several tools around that can be used for modeling aged sorption. People have used tools such as MATLAB and Model Maker, and that works perfectly well. The easiest tool which we would recommend is the Pearl NEQ model. Pearl NEQ was developed by Altera, and it can be downloaded from the Pearl website, which is shown here. What I'm showing you here is the input file for Pearl NEQ. The input file contains the variables that describe the lab experiment, such as the amount of soil in the sample, the moisture content of the soil, and the volume of solution that was added for the calcium chloride extraction. Then if we scroll down the input file, we then get to the part where we enter the results from the lab study, the lab measurements. So here is where we list the pesticide residues at each time point and the concentration that was measured in the calcium chloride solution. Then if we run Pearl NEQ, it will fit the model to give the best description for this data set. So both the residue decline and the concentration in calcium chloride will be fitted simultaneously. The example I'm presenting here is one of the data sets that was provided by ECPA for the development of the guidance. And this is also one of the examples that was used in the EFSA opinion on aged sorption. And the model fitting in Pearl NEQ would need to be done for each of the soils that was included in the study. In this case, there were 4 soils included. We've got soil 6A, 6B, 6C, and 6D. And Pearl NEQ gave a very good fit for each of these model sets, each of these data sets. And then Pearl NEQ also gives the parameters that were fitted to describe the data. Now, before we can use the fitted parameters in our groundwater assessment, we need to check for each of the data sets if the model fit in the parameters are acceptable. And there is a couple of criteria we need to pass. First, we need to check that the model gives a good visual and statistical fit of the data. Just like in degradation kinetics, we calculate the chi-square, which is used as the statistical measure for the goodness of fit. So this example you can see gives a very good visual fit, and the chi-square was 1.9, which is also a very small number and indicates that it's a very good fit. So in this case, the data set clearly passed. And secondly, we need to check if the fitted parameters are reliable. If the confidence interval of a parameter is too large, then this means that the estimated value would be too uncertain and it would not be accepted. The criterion that is used by the guidance is the RSE, which stands for Relative Standard Error. And the RSE will need to be, is not allowed to be larger than 40%. So this is equivalent to a confidence interval of plus or minus 80% around the estimated value, as shown here in the picture. If the distribution would be any wider than shown in this picture, then the parameter would not be accepted. And then the final criterion is we need to check that the experiment gives a clear evidence that aged sorption would have occurred during the lab study. To test this, we need to plot the KD. We plot the KD against time, as is shown here in this graph. The KD is simply the ratio between the adsorbed concentration and the concentration in calcium chloride at each time point. So it's calculated from the mass balance in each sample during the calcium chloride extraction. We test for aged sorption by trying to fit the simple equilibrium sorption model. And we do this, we can do this in Pearl NEQ. There is a switch in Pearl NEQ that allows you to fit the equilibrium sorption model on its own, and it switches off long-term sorption. You can see here in the graph that the equilibrium model did not describe the increase in sorption very well. So this clearly didn't work in this case. We then compare the two model fits, the equilibrium model on the left and the Aged Sorption model on the right. The Aged Sorption model gave a much better description of the increase, and also the chi-square of the model fits is much smaller. So for this data set, there was a clear evidence of Aged Sorption, and the data set passed the criteria. So we need to check the criteria for each of the data sets, for each of the soils that were included in the study. So if any of the data sets fails the criteria, then we would need to set the Aged Sorption parameters from this soil to 0. In this example, all the 4 data sets passed, and we were able to use the parameters from each of the 4 soils. And then we calculate the geometric mean of the Aged Sorption parameters to use in the groundwater modeling. If any of the data sets had failed, then we would have set those parameters to 0, and we would have had to include zeros in the calculation of the geomean. Here you have to be careful though, because we need fitted parameters from at least 4 soils. Otherwise, according to EFSA, we would not be allowed to include Aged Sorption in the groundwater assessment. So this is why we would recommend that when you do a study, you would include at least 5 or 6 soils in the study, just to cover the risk that any of the soils would fail on any of the criteria. Then there's one more thing we need before we can start the groundwater assessment, which is the selection of the other substance parameters for input in the groundwater modeling. You saw that in addition to the Aged Sorption experiments, we also need to perform standard batch sorption experiments on the same soils. So we have actually created additional sorption data in addition to any lower tier sorption data that may have already existed for this compound. So EFSA decided that we need to account for all available data when we do the higher tier groundwater modeling. So we need to combine any new sorption data with any existing data. In this example, the batch sorption data was only available for 3 of the 4 soils. So strictly speaking, it would not have been compliant with the current guidance. But as an example, you can see here that all the available sorption data were combined. So the new data in green and the already existing data in gray. And then the overall means are used in the groundwater modeling. The same needs to be done for the degradation data. By doing Aged Sorption incubation studies, we would also be creating new degradation data for each of these soils. And these need to be combined with any existing degradation endpoints that already exist for the compound before calculating the geomean. So depending on which model we fit to the data, we can either derive the normal DECT50 by fitting the normal degradation kinetics to the residue data, or we can fit the DECT50 EQ by fitting the Aged Sorption model. Any existing DECT50 from the previous studies, here shown in gray, we would need to convert into a DECT50 EQ before we can combine them with the other DECT50 EQs. And this can either be done by refitting the data using the Aged Sorption model, or the alternative is to use a conversion factor. And both of these methods are described in the guidance. So then once we have the endpoints for the higher tier assessment, then the final step is quite easy. Both Pearl and Pelmo provide the option to include Aged Sorption when you enter the sorption parameters for the substance in the model. In Pearl, the parameters are entered here at the bottom of the page under non-equilibrium sorption. And here's where we enter the rate coefficient, the KDES, and the factor FNE. You have to remember that in addition to entering the non-equilibrium sorption parameters here, we would also need to replace the DECT50 in the model by the DECT50 EQ, which is needed to account for the part that is excluded from degradation in the Aged Sorption model. Now these are the results. This graph shows the groundwater packs that were calculated in Pearl for this particular example substance. The blue bars here show the lower tier assessment, which showed exceedances for 5 out of 9 scenarios. And then the red bars show the packs that were calculated after including Aged Sorption. For this substance, the improvement was quite substantial. We reduced the packs by at least a factor of 5 or 6. So that was a very good result. Of course, not all substances will show such drastic improvement as this example. So the question will be, how much improvement can we expect when we want to do adsorption for a new substance? Before we invest in doing an adsorption study, we would like to have an idea whether it may work. Is it going to give us the amount of reduction that we need to pass the risk assessment? The graph shown here is another example where adsorption didn't help to solve the groundwater assessment. After adsorption was included, the packs were lower, but still not low enough to pass the assessment. Now, considering the size and length of the study, this may be an important question to consider before starting an adsorption study. It would be helpful if we could check if the groundwater assessment in principle could be solved by adding adsorption. If the issue is caused, for example, by slow degradation, then the increase in sorption may not always help. We can check this quite easily in advance by performing the groundwater simulations using a range of possible adsorption parameters. Based on existing data for a range of soils and substances, we already have an idea of the range of adsorption we may expect in general. And based on this, we could then run the simulations to test the range of outcomes that we can then expect for any particular substance. One caution, of course, we can never predict the results of any experimental study. There's always some risk involved. For example, maybe not all the soils in the study would pass the criteria. So as I already said, one precaution would be that we would then include at least 5 or 6 soils in the study. And then there are some other things we can do to improve the chances of passing the criteria, such as selecting the right sampling time points. And also by adding additional sampling time points, we can help to reduce the confidence intervals. There's a couple more things we would consider regarding when you would use adsorption. Adsorption can also be used as a higher tier solution for metabolites. In that case, you would need to do this study by applying the metabolite as the test item. In previous research, we tested if you could model the metabolite when it's formed during a parent applied study, but we found that causes too much uncertainty in the parameter fitting. So we would only measure it in a metabolite applied study. The current guidance only covers lab studies, so you can only measure adsorption in lab studies. It does not allow us to use adsorption from measure adsorption in field studies to use in the risk assessment. And this is because there is additional complexity in the fields, and it is just more difficult to derive parameters from a field study. It is easier and more reliable to measure it in lab studies. There are situations, however, when a substance shows faster degradation in the field, and then you would use the field Acti50 in the risk assessment. And in this case, you would want to use adsorption from the field, adsorption from the lab study, and combine it with the faster degradation in the field, so with the field Acti50. In the work we presented to EFSA, we provided a method of how you would then convert the field Acti50 into a Acti50 EQ, so that we can then combine it with adsorption modeling. But EFSA found that there were still some unanswered questions that needed solving before they could accept this approach. So for the moment, the guidance does allow to combine adsorption with field Acti50, but the method it describes is a conservative approach. And the problem is that it does not always give enough improvement over the lower tier. So it is possible to combine it, but the benefit may be small. So again, this is something we would want to look into before we start the study. Now, even with the guidance finalized, there is still some work in the pipeline for Aged Sorption. Together with ECPA and Battelle, we will be continuing our work to improve the procedure for combining field half-lives with Aged Sorption. So that's one thing we will be looking at over the coming months. Another suggestion that was made, now the guidance is finalized, is that we need a more complete tool for Aged Sorption modeling. You've seen that there were quite a few steps involved in the modeling and the decision making, and ideally there would be a user-friendly tool that would automate all the steps, including the kinetic modeling, using the different models, and the decision making, and then the selection of the final parameters for the groundwater modeling. And the development of such a tool is not expected to be anytime soon, but it is on the wish list. So for future developments, and people have now started looking into the options. So now I would pass you back to Chris, who will now tell you a little bit more about possible strategies for Aged Sorption studies.
Thanks, Wendy. So I was really only going to talk about two concepts when considering Aged Sorption strategies. One where lower tier fate data is available and one where it's not. When this data is not available, then consideration might want to be given to combining the determination of soil degradation and Aged Sorption into a single experiment. In order to use Aged Sorption refinement, then at least 4 soils need to demonstrate Aged Sorption. Therefore, we would recommend using at least 6. A minimum of 6 time points are required for the parameter fitting as described by Wendy, and some of these can be lost during the data analysis. Therefore, we are also recommending that you use 10 time points. With the Aged Sorption expertise at Fera and Enviresearch, all aspects of the requirements are covered, and the experimental work would be supported by the modelers to optimize the outcome. Once the studies are completed, modelling reports would be generated, and it is anticipated that 2 would be prepared. One, based on the batch equilibrium and Aged Sorption data, where the Aged Sorption parameters would be established, and a second, based on data from the Aged Sorption study, where degradation kinetics would be established. The second strategy is if data is available from lower tier fate studies. Here, we would suggest a review of the existing data is performed, and some of the things that would be considered are is there is any pH dependency on both the degradation and adsorption behaviour, and consideration of whether the studies themselves previously had any mass balance issues, and also to determine the appropriateness of the available analytical methods to meet the 95% criteria. Based on the experience of the team, a scoping assessment can also be undertaken by considering potential Aged Sorption parameters based on the lower tier sorption and degradation data available. This can be used to determine the potential power of the Aged Sorption refinement available. Experimental studies would then be performed as described previously, with the batch equilibrium and Aged Sorption study performed using soils from the same batch. The same modelling reports would then be produced. As well as those 2 strategies, there are additional services that may also want to be considered when planning your Aged Sorption strategy. A preliminary experiment may want to be considered, which can provide information on the likely rate of degradation to appropriately established time points if this information is not already available. It could be used to aid soil selection, as well as provide an indication of the likely extent of Aged Sorption. As described by Wendy, it's not possible to derive Aged Sorption parameters for metabolites where the parent compound has been applied, so you may want to consider a metabolite study. EFSA's OECD 106 checklist could also be applied to the batch equilibrium data, and our modelers could also use the data generated in the Aged Sorption studies to refine your groundwater modelling. So in summary this afternoon, we've provided you with an overview of the guidance development, taken you through the required experimental design, presented the Aged Sorption model concepts, discussed how you derive the Aged Sorption parameters and use them in the groundwater assessment. We've then gone on to discuss what should be considered when planning Aged Sorption. And we've ended the webinar by providing you with some Aged Sorption services that are being jointly offered by Enviresearch and Fera. We're here to help with your Aged Sorption requirements, and contact details are provided on the final slide. I believe we've now got some time for some of your questions.
Well, thanks, Chris and Wendy, for a really interesting and detailed discussion there around Aged Sorption. We have had some questions come through, so perhaps I can start with one for Chris. Would it be possible to use the standard test soils we always use for OECD 106? And if so, could we then do the Aged Sorption study on the same soils so we don't have to repeat the batch sorption study?
I don't think there's any reason why we can't use soils that are used in a standard sorption study. You know, as long as they show the range of properties, I think that should be okay. But you know, Aged Sorption, like soil degradation, the soils need to be field fresh, used within 3 months. You know, quite often for standard sorption studies, soils are dried and stored for longer periods, so they couldn't be used. And I know it does seem, repeating the 106 initially seems like a waste of time, but when you look at the guidance and the opinion, EFSA have been very clear that you need to think about the soil forming factors. One of those soil forming factors is time. Another one is human activity. So really, to consider soils being the same, I don't think the name or where they've been collected from is suitable. They've really got to come from the same batch. When soils are collected at different time points, even when we do analyse them, we never really get the same result. So unfortunately, I think it's going to be really difficult to avoid repeating the batch equilibrium study.
Thanks, Chris. Question for Wendy. Can we use Aged Sorption for substances that show a biphasic degradation?
Thank you. Yes, we can. We know that Aged Sorption is one of the main reasons why we sometimes see biphasic degradation. So if biphasic degradation is caused by Aged Sorption, then the Aged Sorption model should be very capable of describing this behavior. It should then give quite a good fit of the biphasic decline of the residues. So yeah, in that case, Aged Sorption would work really well. Of course, if it's caused by something else, if it would be like an artifact that causes biphasic degradation, like if microbial activity declines over time, then the data set would be rejected, but otherwise it would work fine.
Thanks, Wendy. There's another question for you here. Do you think there will ever be the possibility to use default parameters for Aged Sorption as we do for plant uptake?
Yes, we have looked into this, but yeah, the answer is actually no. We have during our research, well, the default values were initially suggested in the groundwater guidance, and during our research we looked how the default values represented the spread in Aged Sorption parameters we found, and we found that the default values were actually quite conservative. So there would have been a good solution, especially for soils where we would not, where we fail one of the criteria. So especially when we see clear evidence of Aged Sorption in a specific soil, but for some reason we can't derive clear parameters, then we would have liked to use the default parameters as they are conservative enough. And so like there would have been like a worst case estimate in that case. But unfortunately, EFSA decided that because it is higher tier, that they would only want to use properly measured parameters, so passing all the criteria and no default values.
Thanks, Wendy. Another one for you here. If there is a valid argument, could aged sorption parameters be used for surface water modelling, especially for drainage scenarios?
Yes, it is possible. We had neglected this in the beginning because we thought that for surface water modelling, it is often the short term that is more important. So because aged sorption becomes more important for long-term leaching, it makes more sense to use it in groundwater modeling. However, if for some substances that are quite persistent, you may be using it in spring or in summer, and then it is still present when drain flow kicks in autumn. And in those cases, aged sorption would help, and it does make sense to use it in those cases because, of course, aged sorption would in reality would help to make the substance less mobile and therefore less vulnerable to drainage in autumn.
Thanks. Okay, let's have a question for Chris, I think. Chris, do we expect any difference in aged sorption extent between lab and field studies?
It's a good question, and I'm not sure I've got the answer to that one. Yeah, I mean, I think it's possible. Obviously, it's very clear how we perform the aged sorption experiment in the laboratory and do the. And I'm not quite sure. I haven't given any thought actually to how we perform and get the same data from the field data. So maybe I can have a think about that one and come back with a more thoughtful answer.
Absolutely, yeah. We'll get back to all our participants with answers to their questions if we're not able to answer right away. One more for Wendy. Is it possible to use aged sorption refinement in the case where a substance exhibits pH-dependent sorption or degradation behavior?
That is a good question. We have a think in the current guidance. This is something that EFSA said in their last opinion. They were concerned that aged sorption would be something that is mainly caused by hydrophobic adsorption, and that we don't have a very clear understanding of other types of sorption when pesticides are absorbed in different ways, and one of these this is also the case for pesticides that show pH dependent sorption, that we don't have that good an understanding of how these absorb. But so in the guidance at the moment, it says that you should not use aged sorption for pH-dependent substances. However, we know that aged sorption does occur for all substances because we know that it is caused by diffusion into soil particles and soil aggregates. So this diffusion would always occur for no matter what sorption mechanism is responsible for sorption. Because even if it absorbs on oxides or clay material, these will be encapsulated inside particles or inside aggregates. So diffusion is always an important factor in time-dependent sorption. And if we can measure it properly, then I don't see any reason why we shouldn't be able to use it for pH-dependent substances.
Thank you, Wendy. Well, I think in the interests of time, we're going to wrap up now, but it just leaves me to say thank you very much to Drs. Chris Sinclair and Wendy Van Beinum for their time and expertise today. Thank you all for attending this webinar and for your interest. If you'd like any more information on this topic, you can use the contact details that you can see on your screen to contact either Fera or Enviresearch. And as I mentioned previously, we'll be getting back to you with answers to any of the questions that we've been able to answer during this session. We'll also be sending around a link to a recording of this webinar so you can review it again. But once again, thank you all very much for attending. Thanks to Chris and Wendy, and we'll see you again soon.